So the equations for Boltzmann distribution. If I have a system with n molecules and I have a series of energy levels, u sub j up to t number of levels, I'm starting at 0, always start at ground state. The number of particles n sub j that have energy u sub j of any given, the jth level at equilibrium would be given by, here's that equation. This is the probability of a molecule being in the jth energy level. What's the probability that any given one of my double bonds is in any one of these states? And I might not know this. That's okay. I can still use the probability information. What is Q on the bottom of that equation? Yes. It's called partition function, okay? Q is partition function, okay? And it's given like this, all right? It basically looks like the tops, except for you sum over all of the levels. Q is partition function. It is a normalization factor such that the overall probability of finding a particle in any level will be, I should say, less than 1. Or when you sum them up, it'll still total 1. I guess some words are missing there. But if you think about it, this is sort of like the level, and then divide over the sum of all the levels looks a lot like just a probability calc, except we're taking into account energy, right? It's sort of, the top of this equation is like the level of interest that I care about over the sum of all the levels that there are. It looks a lot like a probability equation. It just happens to incorporate energies, temperature, and Boltzmann. Okay. What was the name for this whole term here? E raised to the negative u sub j over kBt. There's a name for that term. Boltzmann factor. Great. U sub j is the energy of the jth level. T is temp in Kelvin. Okay. Make sure you convert. kBt is Boltzmann's constant in joules per Kelvin. Okay. And again, you may need, if I don't give this to you in joules, you may need to get into joules. If it's kilojoules, make sure you multiply through by 1,000. Always be minding your units. What are the units of partition function? Make it so it's unitless. Convert all your units so that everybody's going to drop out. Joules over joules. Joules over Kelvin times Kelvin, everything should be gone. The Boltzmann distribution helps us see which energy levels of a system will be occupied at equilibrium and for a given temperature. What happens to Q as temperature goes up? It goes up. Okay. Those are the only two options, up and down. So you got a 50-50 shot. The other way to let yourself do it is think through it. It's tough because it is a negative exponent and it's on the bottom of a division sign. So it's, but stop and go, okay, if t gets bigger, this whole term, ignoring the negative sign, would get smaller. Okay, the bottom of my quotient is getting bigger. So the whole term gets smaller, but it's negative, so it's getting less negative. It's actually getting bigger overall. Right? It's a smaller negative number. Okay? The whole term gets bigger, e raised to a bigger thing is bigger. What that means is if I ask you to calculate partition function at a temp, and then I say, now you've raised the temp of your system, you have to recalculate Q. Okay? Partition function is for any given temp. If you're at a new temp, calculate Q again. All right? What happens if U goes up? What happens to Q if U goes up? Goes down. This one's a little easier. It's on the top. Okay. And what about as the weighting factors, G sub j, go up? It goes up. Okay? So know what happens to Q when any one of these things changes. The derivations for these equations are 364 and 365 in your book. They do not do weighting factors, but it's way more relevant for us from a molecular standpoint. So these are the only versions of the equations you have on your equation sheet. Okay? The book, they look identical. J sub g is missing. Okay? they consider 1 across the board. Everything is only possible in one way. Okay. So we've established how delta U and T affect molecular occupancy of the different levels, okay? As U goes up, or as the spacing, delta U gets bigger between levels, okay? Less levels will be populated. As T goes up, more levels will be populated that are higher. If you fix those things and you change the number of different microstates that satisfy the same macrostate, or the same macrostate being the energy level you're at, this is your weighting factor. So for this example here, okay, there's energy here and it's just 0 is the ground state. Epsilon naught is just the energy of the first level and 2 times that is the energy of the next level. What is the weighting factor, or G sub j, for the ground state? It's 4. How about for the first state? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 11. Is it 11? Yeah. How about for the next one? I don't know, it might be 27. I can't remember. I don't have it populated. You're counting the number of different ways to be at the ground state. Okay? I didn't put it in here, I gotta add it. There's a link to a lecture at Stanford University where they go through, like, he proves how to get every single one of these. And I'm like, ugh, don't think through them, that's way too much. Like, one of their example problems is like making you figure out all the ways that it could be, that you could unfold this like 6-mer toy model into the second state. No. What is n sub j? Or what is n? I have no idea, it's not given. These are the weighting factors for the different levels. The total number of these things I'm talking about isn't indicated anywhere here. Okay? So this version of partition function from your book is called canonical partition function, reduced form, classical form, a lot of different ways you might see it online, okay? And again, it's assuming that each energy level has exactly 1 configuration, right? We care about molecular partition function, okay? It's much more practical for the systems we care about. And so it has a weighting factor to accommodate degeneracy, different ways to be at the same energy state. So here's a simpler, instead of the 6-mer model, it's a 4-mer. And if you go ahead, this is the compact form. If you break one of the bonds and open it up, there are 4 different ways to do that. You'd be in the first excited state. Okay? So this whole first excited state is a macrostate, and this one here is one of the microstates. Right? Yes?
So we consider each energy level in the,
what's the other word? Yeah, that.
This.
Canonical, thank you.
so each energy level is a microstate in that case?
Each energy level is a macrostate, and each of those macrostates has only one microstate for this one here. Every level, there's a ground state, there will be a first state, there'll be a second state, and those are different states, but there's only one way to be in them, okay? This one has 4 different microstates that satisfy the same macrostate of first excited energy level. Yeah. And this one, it's just treating all the weighting factors as 1. This is the version from past slides that I used, and sub j was wildly confusing, given that it was also number of particles in the level. So I dropped that and went with what you'll find most often on the internet. So it's cool if you want to look at old materials, even stuff I put together, just be aware of what we're doing this semester. Right? So if you want to write Q for this one, here you go. Weighting factor for the ground state is 1. E is raised to the ground state's always 0 energy. I don't really have to finish out kBt or temp here. Anything raised to the 0 is going to be a 1. 1 times the weight factor is always, the first term of Q is always the weighting factor of the lowest level, the ground state. Then there's 4 ways to be in the first state, times E raised to, my energy was just given as epsilon, I don't know what it is. I haven't been given to me, over kBt. Okay, but if I'm given different energies and different temps, I could go and start plugging this in and using this. Okay. What does degeneracy do to Boltzmann, which is the expected distribution, if you have our assumptions of even spacing? What does degeneracy do to Boltzmann distribution? it messes with it, and we don't know what that looks like. It depends on the system we're talking about. It depends on the nature of the problem we've been given or the nature of the model we've written for ourselves, right? The first 4 problems on the homework are, again, me saying, all right, if I knew the elasticity of a polymer would influence how it would fold and what type of energy it would have, how could I write a model for the energy distributions? Okay? And eventually you just do it with a computer anyway, but you know, degeneracy changes what happens to Boltzmann. What happens when the energy spacings are uneven? Same thing, it no longer looks like an exponentially decaying function perfectly like this, but these equations are still valid, okay? Go ahead and use them. What this is still describing is what the probabilities of the levels would look like. And now it's just taking into account that there are different values for you and there are different degeneracies for each level. But it'll still give appropriate answers for probability if you were to wait long enough and let equilibrium come.